According to Newton's theory of gravitation, the gravitational field around the Earth varies as square inverse law, and this field is radial and directed to the Earth's center. When we zoom in on Earth's surface, the distance considered is so tiny compared to Earth's radius, the gravitational field almost stays constant. Therefore, for practical purposes, we can consider it constant. So let us throw a ball vertically upward. Notice an arrow representing the gravitational force acting on the ball. As we can see, the velocity of the ball continuously varies. First, it decreases until it reaches its peak, and then gravity starts pulling it down, and its velocity starts to increase in the downward direction. Let's see what happens when we throw a ball at an angle. The object's velocity can be resolved into two components, horizontal and vertical. Gravitational force always acts vertically. So, the horizontal component of the ball's velocity never changes, only the vertical component changes. So the resultant vector of the ball changes due to a change in vertical velocity, not horizontal. This is the path of the ball resembling a parabola. Let's analyze this more closely and see how variation in vertical velocity affects the shape of the trajectory. Initially, the horizontal and vertical distance traveled by a ball over a certain time interval is shown here. The resultant displacement will be as shown. Since the horizontal component of velocity doesn't change over time, the ball will travel the same distance horizontally over equal time intervals. However, the vertical component of velocity is reduced due to gravity's effect. Thus, the distance traveled vertically in the same time interval will be less. Applying the same logic across certain time intervals, we observe the object following a curved path. At the peak, the vertical velocity reduces to zero, and so does the vertical distance traveled. At this point, the ball reaches its maximum height, after which it begins its descent as its velocity continues to increase. In real-life motion, since it is continuous, decreasing the time interval from the previous consideration results in a closer approximation to the actual motion. Now, let's derive the equation of projectile motion. A ball is thrown in the air at an angle theta. Velocity of the ball can be resolved into two components, u sine theta and u cos theta. Force of gravity always acts vertically in a downward direction. The path of the ball resembles a parabolic shape. To find out the position of the ball xy at any instant, we have to derive an equation of the parabola representing its motion. Here, the x-coordinate of the ball is affected by the horizontal component of velocity, and the y-coordinate of the ball is affected by the vertical component of velocity. So we can treat both conditions separately. First, we have Vx equals u cos theta. There is no force in a horizontal direction. Finding the x-coordinate of the ball is pretty straightforward. Now we have Vy equal to u sine theta minus gt. Because of the force of gravity, Vy changes with time. So we can find the y-coordinate of the ball with integration, considering the initial position of the ball to be at the origin. Note that both equations are parametric to the variable t, that is, time. We can change it into a single equation by substituting the value of t in the form of x. So this is the final equation describing the motion of a ball thrown at an angle. Now let's calculate the time of flight and horizontal range of the ball. Time of flight is solely dependent on vertical velocity. Upon landing, the vertical velocity becomes the negative of the initial velocity. The final expression for the time of flight is 2u sine theta by g. The range is dependent on horizontal velocity and the time for which the ball stays in the air, which is the time of flight. Since horizontal velocity is constant, multiplying these two gives us the horizontal range. The final expression for the horizontal range is u squared sine 2 theta by g.